all my rubrics this morning, and the photocopier decided to run out of toner. That was at 10:30. They have not put any toner in there yet. So I am still waiting for quite a few. So these ones are done and ready. I have a pile on the floor in the office waiting for the printer to suddenly come back to life, which might happen before the end of class or might not. So what can I say? Kim, Troy. That's nice. Yeah. He's not here. But thank you.
I used to say one last next to you.
Lawrence isn't here, Blake's not here, Kevin's not here. All right, let's see if we can get this chapter on the video. All right, so we were looking at pressure gradients on Monday, and how the fact that the high to low, that the pressure differential aids the movement of gases, oxygen on the way in, carbon dioxide on the way out. So now we want to look at, now we've got the oxygen out of the alveoli and into the bloodstream, how is it moving around? Right? So although blood has a high percentage of watery substance, the plasma, actually oxygen doesn't dissolve very well in that fluid. Right? So very little of the oxygen that we take in gets dissolved and moved around that way. Most of it has to be picked up by the red blood cells. All right? Red blood cells contain a molecule called hemoglobin. It's heme because it has iron in it, and that plays a role when we look at people who are anemic. All right? So we'll come back to that idea. So the hemoglobin has to have an iron for it to do its job properly, and it picks up about 98% of the oxygen that we take in. Okay? If the hemoglobin has oxygen attached to it, we call it oxyhemoglobin, and if it's free of oxygen, it's deoxyhemoglobin. So the most beneficial position is to have all our hemoglobin bound to oxygen. That's called saturation. Right? So if we can have all our hemoglobin carrying oxygen, then that's our capacity. That's the most we can transport at that point in time. Right? So if we think of it that way, then the concentration of hemoglobin that is available determines how much oxygen can be moved around the body. All right? So having very little hemoglobin, or having hemoglobin that isn't working correctly because it doesn't have an iron in it, impacts that oxygen transport. So iron deficiency, the primary, if we look at anemia, anemia is going to be because of either a deficiency in the red red blood cells, which can happen if there's something wrong with the bone marrow in the long bones for adults. So sometimes you hear about people needing a bone marrow transplant. That's typically because their bone marrow is not producing red blood cells correctly, right? But anemia can also occur if there's a problem with the hemoglobin, for example, if iron's not available, or some combination thereof. And that decreases our ability to carry oxygen around to the muscles that are working. All right? And without the oxygen, remember the hydrogen, if I'm working aerobically, that hydrogen is going to come down the electron transport chain, and we're going to end up at the bottom of the electron transport chain with a pile of hydrogen coming out and no oxygen to pick it up, and then we get an acidic environment and ATP production will slow down. All right? So it's severely, developing some form of anemia severely impacts endurance aerobic events. All right? The typically iron deficiency is a lack of intake, so people don't like to eat, in America, liver, for example. You don't drink anywhere near enough Guinness over here. Green leafy vegetables are good for iron, all right? So not taking in enough iron can be a problem, but another problem can be absorption. So you can take in enough in your diet, but something doesn't work right with absorbing it from the intestines. And so then we have the same problem. If the iron's not available for the hemoglobin, then the hemoglobin can't do its job and pick up oxygen properly. All right? If you work with female athletes, if you have female athletes who basically hemorrhage, have very, very heavy menstrual cycles, then their aerobic capacity might be diminished for a few days around that time. Pregnancy can cause iron deficiency because the body will divert the iron to the baby. So then if you don't intake more, then you can become anemic because you're pregnant. So another long, horrible word. I don't know what it is about ex-phys and the long, horrible words. Can't just make them short and sweet, right? One of the things we have to take into account is if I've got this oxygen loaded onto hemoglobin and it's just floating around my bloodstream, how does my body know at what point in my body it's supposed to offload the oxygen to the muscle, right? Because it's like on the bus, trundling around, how does it know where the bus stop is to kick it off, okay? And this horribly named curve is an attempt to visualize the ability to bind oxygen and release it at the right place. All right, and again, it's one of those, if curves are not your thing, then you might just have to try to understand the idea of it without the curve. All right. What it's trying to show, so this is the partial pressure of oxygen. So remember that the partial pressure of oxygen is quite low in the veins coming back to the heart, all right, because it's given up a lot of its oxygen at this point. All right, so we don't have a very high percentage of saturation in the blood that is coming back to the heart. All right. Then it picks up a lot of oxygen at the lungs, and it becomes fully saturated. And this is in the arteries now. We're at 100% saturation. And that's the point at which we can drop off oxygen to the working tissue. All right? So how does it know to get off the bus? Okay? So one of the things that happens when we exercise is that the temperature in the muscle that is doing the work increases. All right? And an increase in temperature shifts the curve to the right, which decreases the affinity or the bond between hemoglobin and oxygen. All right? So again, if the curve thing does your head in, ignore the curve. Right? If you're okay with the curve, the temperature shifts it to the right. What that indicates is that I can get rid of my oxygen more easily. Right? The oxygen can get off the bus more quickly. Right? When I'm cold, and one of the reasons that we have to do a good warm-up before we exercise is because when I'm cold, the curve shifts to the left, and that increases how tightly oxygen is bound to hemoglobin. Right? So it's like when I'm hot, the bus drives along with the doors wide open and the oxygen can fall out the door. And when I'm cold, the bus locks all the doors and the windows and the oxygen is trapped on the bus. Right? So we can't exercise efficiently when our muscles are cold because the oxygen has a harder time getting into the muscle tissue and being available for ATP production. Right? So we have to warm up those muscles so that we can improve oxygen delivery to the muscle cell. Okay. So that's one thing that happens that helps with hemoglobin dumping oxygen at the correct time. Right? Another one that occurs has to do with our pH value. Okay, so when we exercise, even if we've got oxygen available, the pH in the cell is changing. All right? So if I see an increase in acidity, my hydrogen ions go up, which is what is happening in the cell when I exercise, the curve shifts to the right. It's easier to move oxygen into the muscle cell. Okay. If I decrease the acidity, so when we're at rest, the curve shifts to the left and it's harder to unbind the oxygen and the hemoglobin. All right? The textbook talks about a third mechanism. Ignore it. I can't even say the word. Ignore it. All right? What you're looking for to ignore is 2,3-DPG. And that word I'm not going to attempt to say. All right? So when you get to this point in the chapter, they'll talk about 3 mechanisms. I want you to concentrate on the temperature and the pH. All right? Ignore the other one. All right? So the take-home message is when the muscle is exercising, we see an increase in temperature and an increase in acidity and an increase in oxygen delivery off of the hemoglobin. Yes? Okay. All right. So, an increase in temperature increases the ability to deliver oxygen to the cell. Right? The technical term is that it decreases the affinity of hemoglobin for oxygen. But decreasing the affinity means I'm increasing the delivery. Okay? So if I increase the temperature, I have the ability to increase the delivery. I can kick more oxygen off the bus. Right? If I increase the acidity level, which we do when we're exercising because we're releasing hydrogen ions, I increase the ability to get oxygen off the bus. Right? So maybe think about it like this as you're reading it. Right? Increase delivery is exactly the same thing as decrease affinity. Right? Decreased affinity just means that hemoglobin isn't as able to hold on to its oxygen. So it increases delivery because it can't hold on to it anymore. And vice versa. Right? Decreased delivery would be increased affinity. Does that help? So just settle that, blah, 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 blah. That's moving left and right. We've done the Bohr effect, we're ignoring that one. Okay. So I deliver the oxygen to the muscle tissue. If the muscle is working aerobically, it is going to be creating carbon dioxide, which needs to be removed, right? Because it's not useful. So we have three mechanisms for moving that carbon dioxide from the working muscle tissue back to the lungs so that we can breathe it out, okay? A little bit of it, again, not very much, can be dissolved in the plasma. Some of it can bind to hemoglobin, which seems a little contradictory because I want my oxygen bound to my hemoglobin, but actually they bind to different parts of the molecule so they don't interfere with each other. Okay? The vast majority of carbon dioxide gets split and transported as a bicarbonate and then reformed when it gets back to the lungs. When it gets split to bicarbonate, that releases hydrogen, which increases acidity, which helps dump more oxygen. Right? So the body has all these clever interacting systems going on that benefit each other, particularly when we're exercising. All right? But in the main, for this class, it's not that we're not interested in the carbon dioxide removal, but the oxygen delivery, because that's our ATP production, that's our muscle contraction. Focus more on oxygen than on carbon dioxide. You can't ignore carbon dioxide, but it's the back to front version of oxygen when you're looking at pressure gradients. Because it's moving in the opposite direction. All right. So, let's make this a little less complicated. Here's my red blood cell. All right. Here's my respiratory membrane. All right, so this is my lung. Okay. And then let's pretend, they haven't got that on there, but let's pretend that this is our muscle. So, air in the lung has high partial pressure of oxygen, right? When the hemoglobin, when the red blood cell reaches the lung from the right ventricle, remember, okay, it's low in oxygen at that point, because it's traveled all the way around the body and all the organs and tissues that have needed oxygen to make ATP have depleted the oxygen levels, all right? So this is relatively low in VO2. That means I can move oxygen from the lung, from the alveoli, into the bloodstream and attach it to hemoglobin in the red blood cell. Yes? Okay, now, that same level then, once I've got it attached, this is now high, and the muscle is relatively low. Okay. So now I can move oxygen off the hemoglobin, especially if we take into account temperature rise and acidity rise, that is benefiting shifting the oxygen off the hemoglobin. Okay? So our dissociation curve is occurring here. Right? So you have to remember the high-low is not a number here. The high-low is this in comparison to the other side of the membrane. Right? So this number could be 5. It can still be 5, but 5 is now higher than it is in the muscle tissue that is 3. Right? And numbers are arbitrary. Okay? So we're working aerobically. We are making carbon dioxide. So it's relatively high in the muscle tissue, and it's relatively low in the bloodstream, and so we are able to move carbon dioxide into the bloodstream. And as I said, it gets split into bicarbonate, and the version in the textbook has all kinds of complicated, splitting it into bicarbonate, HCO3, or it's a long time since I did chemistry, whatever that is. All right, keep it simple. Okay. When I get to the lung, this same level of carbon dioxide is now high compared to what I'm breathing in and what is in the lung. All right. And as I said, if this hemoglobin has oxygen on it that hasn't been offloaded yet, and it's traveling around the body, it can still pick up carbon dioxide because they don't attach to the same portion of the hemoglobin. Right? So they're not in competition for that space for the bus. Okay? Remember one day I said this wasn't the right version of this PowerPoint? It still isn't the right version of this PowerPoint. I don't know why I'm doing it. Okay. All right. The next little piece of the picture then, I've got oxygen from the atmosphere into the lungs. I've got it from the lungs into the bloodstream. I have a bus mechanism that can transport it around, and we've got several things in place that move the oxygen off the bus and into the muscle tissue. Okay? Now, this is where we have to go all the way back to the beginning of the semester. Right? If this is my muscle cell, okay, and my oxygen is here, where does system 3, where does aerobic metabolism take place within the cell? In the mitochondria. Well, what if the hypothetically, there's not only one mitochondria in a muscle cell, right? But hypothetically, what if my mitochondria is over there? Right? So now we have another piece of the picture, because it's all very well moving oxygen into the muscle cell, but it can't do any good here. It has to be in here. Right? So we have another molecule that's very similar to hemoglobin called myoglobin. Right? Anything that's myo is muscle. Okay? And it facilitates the movement of oxygen across the cell and into the mitochondria. I said, even though we tend to consider each energy system as a separate, first energy system 1 turns on, then energy system 2 turns on, then that's not really what happens, right? There's hardly any point at which only one system is doing the work. So when you first start exercising, yes, you're mainly going to use system 1 and into system 2, but because of the myoglobin, we've got a little bit of oxygen sitting in the muscle cell. So we can still ramp up our aerobic production of ATP when we get up and run out of the building because the fire alarm goes off. Okay. It's just not very much, but there is some oxygen always available sitting on the myoglobin in the muscle cell. Okay? The other thing that this relates to is that idea of EPOC, that excess post-exercise oxygen consumption. We said that, why are we breathing so hard when now we're not moving anymore, right? One of the factors, if you go back and look at the list of reasons why we think the breathing continues like that, one of the reasons is we have to replace the oxygen on the myoglobin that we stole at the beginning of the exercise. We've got to put it back so it's there for the next time around. All right? Okay, so application question. Which type of muscle fiber has the highest myoglobin content?
Type 1.
Alright, good. Okay, type 1. Because type 1 is the muscle fiber that is best able to use oxygen to make ATP. Right? It's our long distance, continually contracting. All right, doesn't get fatigued. Okay? So it's really good at using oxygen, which means it has lots of myoglobin available to move oxygen to the mitochondria. Right? Type 2As have less myoglobin. Type 2Xs have even less myoglobin. Very little at all. So it's another factor that plays a role in our VO2 max. All right? And our ability to use oxygen at the cellular level, we now have another variable, how much myoglobin is available. So if I have a high quantity of type 2 fibers, then I have less myoglobin available and I can use less oxygen and my VO2 max will be lower than someone who has lots of type 1 fibers. Right? Or if I have lots of type 1 fibers, but I'm sedentary and I don't train them, then their myoglobin levels will be lower. And their VO2 will be lower. Right? Let's do that on the picture. It's easier on the picture, I think. All right, so breathing is an interesting concept because most of the time we're not consciously controlling our breathing, right? And it's one of the few things that we do where we do have conscious control of something that is typically unconscious, all right? Depending upon your philosophical beliefs, some yogis and some yogi backgrounds say we have control of our heart rate, right? I can deliberately, consciously slow my heart rate down. You may or may not believe that, right? Most Western people would go, no, you can't. There's no conscious control of your heart rate. But Eastern medicine would say otherwise. But when we look at breathing, I can't control my digestion, right? I don't get to decide whether my apple is digested quickly or slowly, right? So when we look at breathing, it's really, from a Western point of view, the only thing that is unconscious but can be conscious, right? For a period of time. You can't have conscious control of your breath for very long, okay? So most of the control of your breathing comes from a respiratory center in the medulla, all right? So in the medulla oblongata and the pons in the brain. So that area of the brain acts as the pacemaker for your breathing, all right? And then your rate of breathing, your depth of breathing can be controlled by higher centers in the brain. Also, there are chemoreceptors in the medulla that will respond to that hydrogen, okay? And they will change the rate and depth of breath, or they will send messages that result in breath changing depth and rate, right? You've also got stretch receptors in the lungs, you've got chemoreceptors in the carotid arteries. Okay, there's all kinds of different areas that are sending messages and helping this overall control of breathing, all right? So, if we want to, we can hold our breath, right? For a while. The reason people drown is because you can only hold your breath for so long, and at some point the involuntary control of your breathing will kick back in and make you breathe. And then you breathe in a lungful of water and you drown. Okay? So that's why we can't, you think, oh, I can hold my breath for a long time underwater, and I can train that and I can get better at it, but it's a finite period of time. Your brain won't let you do that, okay? But we can trick it. And this is something that elite level swimmers do, okay? They will, if you watch them when they are waiting to dive into the pool on the go, all right? You can watch an elite swimmer deliberately hyperventilate. Has anybody hyperventilated before? It's very uncomfortable, right? Your lips start tingling, your fingers start tingling, and then you stop breathing. It's very scary. We'll come back to that in a minute. So you don't want to be using this technique with beginners, all right? So what they do is they hyperventilate. So you will see them going, uh-oh. You'll see them going, okay? What people imagine is that they're breathing in more oxygen so that they can hold their breath on the dive, because we're more dynamic underwater than we are once we break surface and we have to be on the surface of the water. So when we dive in, we want to be under the water for as long as possible and get as far down the pool as we can before we have to come up, right? So when you watch this, it looks like they're breathing in more oxygen so they can hold their breath. That's not what they're doing. They're breathing off carbon dioxide, right? So you blow off lots of extra carbon dioxide, and it tricks the medulla into thinking that you don't need to breathe because there's no carbon dioxide to breathe out. And it lets you hold your breath for longer under the water before it makes you breathe. It's very sneaky, right? 2-year-olds do it to their parents, right? They throw a great big raging tantrum and they scream and shout and and then they hold their breath. And the parents are going, come on, breathe, please breathe, breathe, come on, breathe. And they can hold their breath for a very long time, right? Because during the tantrum, they've blown off so much carbon dioxide, the brain allows them to hold their breath for a long time. Freaks parents out. You don't just sit there and let them get on with it. Eventually they will breathe. Just walk away and go, fine. Right? in exercising. I've heard, I don't know the runners amongst you, I've heard that sprinters will do it sometimes so that they don't have to waste energy breathing over the first 25, 30 meters of a sprint. But I've not read anything, so I don't know for sure if that's true. But it's so back to one of the things you have to have in your first aid kit: brown paper bag, right? Because if you have someone start to hyperventilate, then you have to reverse the problem, and you have to make your brain realize there's more carbon dioxide in the system than there should be, and make you breathe. Because when you hyperventilate, it turns off, and you literally cannot breathe. I mean, your whole rib cage just goes solid. It's really scary. If you put a brown paper bag over their face and make them breathe into the brown paper bag, eventually they're going to be breathing in carbon dioxide, and then that will turn this back on, and they'll be able to start breathing. Okay? So, always, 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 in your first aid kit, brown paper bag. Didn't know that, did you? See? Don't use a plastic bag, that doesn't work so well. Don't do that. All right. So when we start to exercise, we see a similar pattern to what happens when we look at the heart rate. All right? We have this initial lift in breathing just before you start exercising, particularly if you're very experienced. It's like your body knows it's coming, and so it starts to get you ready a little ahead of time. All right? And then we see this steep rise in breathing, and then we'll hit steady state. So we will hit a plateau here. Right? And then we stop exercising, and here's our epoch curve, recovery. Okay? So phase one is prior to the start, or around the start of exercise, right? Abrupt increase in ventilation due to anticipation, stretch receptors in the lungs, right? Phase two is a quick rise up to steady state. Phase three will depend how long you stay at the same work rate, the same intensity, right? Because if I change intensity, then I'm going to have to start breathing heavier to deal with the extra workload. Right? So phase three would be fine-tuning that steady state. Just how hard do I have to breathe to deliver enough oxygen for the work that I'm doing? And then we have our recovery phase, which is our epoch curve. So this area of what's going on is related to the carbon dioxide controls and all these respiratory centers. We're not quite as certain what is helping to control the steady state situation. Okay. Adaptation-wise, there's very little adaptation. So this is the acute picture of what changes in my breathing when I start to exercise right now. Chronic changes, adaptation, we really don't see very much. So for people who are not asthmatic, pulmonary ventilation, breathing is generally not a limiting factor for exercise at sea level. Right? Everybody can breathe. And so unless I've got bronchitis or pneumonia or I'm asthmatic, then at sea level, breathing is not a limiting factor to exercise. I don't fatigue breathing, right? My respiratory muscles work like a type 1 type muscle, okay? They're very high ability for oxidative phosphorylation, so a type 3 system for ATP production, and they're relatively fatigue resistant. There's some information that you can train them, so you can make your respiratory muscles, your diaphragm and your intercostal stronger by training. Weight training works your diaphragm a lot. You can go if you're going to run. All right. Weight training is really good for training the diaphragm because all that pressure and it has to hold a lot of organs in place. Okay. When we get to altitude training, we'll talk about the mask situation. Those masks really are not altitude training, they're training your diaphragm and your intercostals. But we'll talk more about that when we get to altitude training. Okay? All right, so Friday, not you guys. The rest of us will have a review on Friday, exam on Monday, exam on Monday,